Now I'll start again. I did want to point out that on page, what is this, 8 of your handout, there are words. So this is a results section that would go with these analyses and how I would talk about them. So we've got the first paragraph that sort of describes the setup, and then what we've done thus far is this paragraph. So how I would talk about between versus contextual versus within. We had observed stressors predicting physical symptoms, revealed significant positive contextual and between person effects, but no significant within person effect. Thus, after controlling for age and sex, but before controlling for negative mood, physical symptoms were higher on average for persons who experienced more stressor days than others, even after controlling for daily stressors. But physical symptoms on a given day were not related to whether a stressor was experienced that day. So that is to say, we have between and contextual effects that are both significantly positive, and then the within effect was actually not significant. So then we did model 2, which is what we just finished, looking at how mood predicts physical symptoms. And the same pattern, significant level 2 effects of both kinds, but no significant within person effects. So we went from X to Y, X to Y, and we went from M to Y. Now we can put it all together with all 3 variables at the same time. So that, I believe, I called that step 3. So then we can see to what extent the relationship between stressors and symptoms and between mood and symptoms differs after controlling for the other variable. So up to this point, I would call these effects mostly bivariate, and now we can look for unique effects at each level. So I am starting on page 6 of example 2. So a lot of code because we're doing a lot of things at the same time. And this, by the way, is the motivation for moving out of lmer or any other kind of univariate software, is when you want to have multiple outcomes at the same time where one outcome predicts another. So mood in this model is going to be both an outcome of stressors as well as a predictor of symptoms simultaneously. So then, in terms of the variables, we are using symptoms, mood, and stress, and the 2 parts of stress as observed variables simultaneously. That means that level 1 stress is treated as a within-only observed variable, and then person mean stress is a between-only observed variable, but mood and symptoms are both going to be partitioned by the model into their level 2 random intercept and level 1 residual variance components. So then I've got 2 separate level 1 residual variances, one for symptoms, one for mood. So that captures all of the fluctuations around a person's mean for both of these M and Y variables. And then I have all 3 of the level 1 regressions that would be needed to form a mediation triangle. So I've got stress to mood, which is X to M, stress to symptoms, which is X to Y, and then mood to symptoms, which is M to Y. And I'm using the placeholder syntax again so that I will end up with within effects and contextual effects for all of these things. Then at level 2, I've got fixed intercept and random intercept variance in Y, fixed intercept and random intercept variance in M. Then we get to the level 1 effects. So that one, that one, and that one. Those are the fixed effects for each within pathway from X to M, X to Y, and M to Y. All 3 of them have their random slope variances associated with that path fixed to 0. And that was because in prior models, none of them were necessary. Then we have women and age 80 and their interaction predicting both Y and M. So we're controlling for the effects of gender on the M and the Y variables. And then we get the corresponding between level effects, which are actually contextual given the way the model is phrased, for x to m, x to y, and m to y. So now we're at the full triangle at both levels. We can create between level effects by adding together each of the within level 1 effects plus the level 2 contextual effects. So then I have new terms being created via model constraint for between level pathways for the 3 parts of the mediation triangle, and for doing indirect effects. So an indirect effect is the multiplication of 2 direct effects from the predictor to the mediator and from the mediator to the outcome. So what I'm computing then first is the indirect effect that's within persons. So this is going to tell me the extent to which the relationship between stressors and symptoms is mediated by mood. I then get a contextual mediation effect that is the same idea, except these are because of person mean differences after controlling for the variables at that occasion. And then I can do the between person version as the relationship among the person means not controlling for each variable at each occasion. And in Mplus, there is a model indirect command. Have you seen that before? Maybe a little bit. You can only use it for single level models though. So that's why it's not in here, because it's not available. So I had to make the indirect effects myself as these multiplicative combinations. The p-value that shows up for these is your typical Wald test p-value. Some people call that the Sobel test. And people who study mediation might yell at you if you look at it. Personally, I can't care. I've decided that there's certain things that I care about and certain things I just don't have room for, and this is one of the latter. I'm just not going to worry about whether my p-value for my indirect effect is as good as it can be. But in case reviewer 3 wants you to care about that, there are various ways you can use bootstrapping to get a more reliable p-value, but in this case you would have to bootstrap the estimates rather than the data. And I would refer you to a calculator on Chris Preacher's website, which is quantsci.org, by which you can do that. So if you ask the Google for him, you will find all of his mediation resources. So I would do that to make sure that whatever p-values you have are going to be the optimal versions in those cases. So this is a complex model, but it's not any different than just literally doing all the things we've done at this point all at the same time. So questions on any of the code or the logic? No? Good? Good to go? All right, let's see what happened. So at the within level, I only have 2 parameters reported. What are these things? What do they represent? Other level. Good guess, but no. These are within levels. These are the E variances, yep. And they are residual because they are level 1 residual variances left over. So this is the remaining within person day-to-day variation in physical symptoms after controlling for whether or not you had a stressor that day and your mood level that day as well. So this is variance left over in Y. Likewise, this is variance left over in M as the mediator. So the mediator is only predicted by stressors in this case. Please.
And would you interpret it somehow? So to me it looks rather large. 6.61 for symptoms significant, would you say then maybe like we're still missing a very serious with in-person predictor for these symptoms or not?
The number itself has to be taken into account with the scale of the variable. So where I would look for that kind of idea would be effect size. So how much of the variability in symptoms is explained by the model and how much is left. And if a lot is left, then that would indicate, yeah, we're probably missing some things. But I don't know what, I mean, you can only put in what you have in your data, right? So this is, you're constrained by what you've collected. But these are unstandardized coefficients, and so we would have to pay attention to scale. There are not standardized coefficients provided by these models. And that's in part because a standardized coefficient, you would need to have the standard deviation of x and the standard deviation of y. Well, which one? You want the level 1, the level 2, the both? And because there's an ambiguity there, it's not something that people typically report. In models where there's a clear delineation of between versus within variance, you can use the corresponding standard deviation to create sort of a pseudo-standardized effect. But these are just variances left over. We would have to know how much they started with to know if this is a lot still. Then we get to the prediction of symptoms. So those are my demographic variable controls. We also have the same age and gender and their interaction predicting the mediator as a control. Looks like none of those matter at this point. Then we have the two contextual between effects for symptoms, and they're both significant even after controlling for each other. So this indicates that people who have more stressors than other people have worse symptoms than other people, and people who are grumpier on average than other people have more symptoms than other people. And these are both after controlling for whether or not you had a stressor that day and your mood for that day, because these are contextual effects. Then we get the stress to mood relationship, and this one is not significant. So it looks like there is no relationship between proportion of days in which you had a stressor and mood after controlling for whether or not you had a stressor that day. So this is the contextual effect again. Here are my three within person effects, and it looks like only one of them is significant, the first one. So x to m, that one's going to tell me that on days where you have a stressor, after controlling for your average number of stressors, there is a relationship between having a stressor and feeling worse that day. But worse mood, I should say, not worse symptoms. So worse symptoms is that one. And there is no relationship between mood and symptoms after controlling for stressors. So we'd want to interpret these in the context of what they were in the previous models without controlling for it. So we can think about whether or not these are unique effects that are non-significant or bivariate effects that are non-significant in the earlier cases. Then we get fixed intercepts for my m and my y, as well as potential random slope variances would be here. They've been shut off for right now. And now these ones, what are these things? Now you got the random intercept variances. Yeah, still labeled as residual though, because they mean leftover. That's what they mean. And I can create between person effects then by adding the within and contextual together, and those are all significant. So there's only one case in which the inference would change. It is, see, m to y, which is, where is it? When did I do that? Not one. That one right there. That's stress to mood, and that one right there. So these both describe level 2 relationships between proportion of stressor days, so as a proxy for sort of how stressed a person is in general, predicting their negative mood in general. And there is a relationship there according to the between effect, but that relationship is non-significant after you control for whether or not you had a stressor that day. So here's an instance in which the between and contextual effects would have different conclusions. Which one you believe, up to you. That this is all I can tell you is that the relationship is non-significant after you control for whether or not you had a stressor that day. That's all. And then the indirect effects, it looks like there is a between-person indirect effect, but not a contextual indirect effect. So I would say that the relationship between stressors and symptoms between persons is partially mediated by negative mood. There. That's not so bad, right? Yeah. Can I make it worse? Yeah, I can. I have the power. No, I was going with a different kind of worse. I was going with moderation. Can you do moderation and mediation at the same time? Sure you can. What if I wanted to see whether or not the relationship between, let me see, which one is this? The relationship between, the effect of mood in predicting symptoms differed between men and women. Could I test that? That's a reasonable thing to test. Now, how to test that? What I'm talking about is an interaction term between a box, which is observed gender, and the random intercept for mood, as well as the residual variance for mood, because gender can moderate both levels of relationship simultaneously. So that requires estimation of a latent variable interaction, which when I first tried to do it in Mplus, it yelled at me. So this is what I tried to do initially in the download folder, example 2 extra. I had to switch the method of estimation to include algorithm equals integration. It wanted me to have that, and I told it I had 4 processors, so it would work a little bit more quickly. And what I wanted to do was to add this part right here. So I wanted to define a latent variable interaction between the random intercept for mood and gender. And so xwidth is the command that allows you to define latent variable interactions. It's considered a latent variable interaction if either of the variables is latent, or both. So I tried to set that up. I thought that that would work, and it yelled at me and said, "You can't do that!" Because it was treating mood 2 as the observed part at level 1 rather than the random intercept that I had intended it to be. The moderation of the level 1 effect can be done, though, directly. So this is an example of a cross-level interaction where the outcome is the relationship between mood and symptoms at level 1. And by saying that women, as a predictor of this outcome, it's akin to saying that we're allowing a different within-person slope between men and between women. So this type of cross-level interaction requires the same placeholder syntax as the random slope. It's just that we're saying that there's no variance left over at this point. We would allow different within-person slopes for men versus women, but not randomly otherwise. But it was this part of the model that it yelled at me for. And here's the error. It says, "You can't do that." I said, "Okay, I'm going to do a workaround." So I put this on the Mplus discussion board, I think many years ago, and got a workaround idea from the mutanes that I have implemented here by tricking the random intercept into being a new latent variable. So what I did in the level 2 model is transfer the random intercept for mood into a new latent variable, which I called mood int for mood intercept, that is perfectly measured by the observed variable. I know. It's ridiculous. But then it let me do it. So everything from this point forward is dealing with mood int as the latent variable that borrowed the information from the random intercept. And then I could do the X with level 2 interaction, which allows different contextual effects by gender, as well as different level 1 effects by gender of how mood predicts symptoms. Had to wait a few minutes for this because numeric integration is more computationally intensive. And so then I get the new terms right here. This is the difference in the within-person slopes between men and women. And this is, let's see, that one is the difference in the contextual effects between men and women. And then I can get to the difference in the between effects between men and women. And none of those are significant, so we don't need them. So that's where I had the results section come in to describe what I had up to that point. Here is how I would write the equation for this multi-level model. So at level 1, I have two separate equations because both mood and symptoms are my outcome. That means that I have two sets of level 2 equations, one for M and one for Y. So the ones for M would have the intercept be predicted by age, gender, and their interaction, as well as person mean stressors. And there is a random intercept variance left over for mood. I have just a fixed slope for the effect of level 1 stressors. For symptoms at level 2, I have the same thing, but this is the different part. So the predictor for mood at level 2 is the beta, not an observed variable. It's not the U, it's not the leftover part, it's the whole thing. And so that part of the notation looks a little bit different when you're doing this latent centering thing. But otherwise it looks like our standard multi-level model, just with two separate outcomes being described at the same time. How are we doing? That's how we're doing. Just think these are resources, okay? These are examples for you to pull from later when you get your head back on you after not having been talked at for 2 days in a row. So then I thought, I wonder if I could treat stress as a latent variable if I switched it into single level SEM. And it turns out you can. So this is the exact same mediation model on wide data as a structural equation model. So after changing the data from long to wide, I have stress 1 to 5 as my X's, mood 1 to 5 as my M's, and symptoms 1 to 5 as my Y's. I'm telling it that stress 1 to 5 is categorical, so it's going to fit a logistic regression type of model to predict that, or what some folks might call an IRT model, dun dun dun, because theta is a random intercept. It's a random effect of some kind. If this is a Roche type model, it's a random intercept. So then the setup for this version of the model, I have to fix all of the thresholds to 0 and all of the observed intercepts to 0 so that all of the information about the means goes up into the latent variables. I constrain the residual variances for mood to be the same, the residual variances for symptoms to be the same, and I don't have one for stress because binary variables don't have separately estimated residual variances. I then define my 3 random intercepts. So I have F for X, F for M, and F for Y, each indicated by their corresponding observed variables, all loadings fixed to 1, which makes them intercepts. I then have my fixed effects estimated for each intercept, their random intercept variances for each one. I have the effects of age and gender and their interaction on M and Y. And then heading into the second column here, I have the level 2 mediation model right here. These are all going to be contextual effects. So X predicting M, X predicting Y, M predicting Y. And then here are the level 1 effects defined very parsimoniously with this lovely option, one of my favorite things, pawn. Have you seen pawn before? There's also p-width, but that doesn't have a pronunciation that's as nice as pawn. What that does is pairwise on. So when Mplus reads this one line, it is creating 5 separate regressions. Stress 1 predicting mood 1, stress 2 predicting mood 2, stress 3 predicting mood 3. So it shortcuts the syntax. And this label out here is both a label and a constraint that says all 5 of those relationships should be the same, because I'm not hypothesizing that the within effect varies across days. So I've got my 3 sets of pawns here, then I can build my between effects, and then I can build my indirect effects. So the output looks different because it's a structural equation model with wide data, but we find many of the same conclusions with respect to what matters at level 1 versus level 2. And then I have a note here just sort of eyeballing this, that it looks like the results are a little bit stronger if you treat stress as latent than if you treat stress as observed at level 2, which is, again, consistent with what we would expect. So you can do this in maximum likelihood to have all 3 have this latent centering type of thing with the random intercept. Ta-da! Sometimes I feel like this is like a video game and like I just beat the game. You know, when you can finally make it work. You know, like I've killed Bowser in his castle or something. Killed all the zombies in Minecraft. Trying to think of all the games that my son plays. He's addicted to screens. So again, resources for later, but there are multiple ways to approach a problem, and if one way doesn't get you everything you want, you can try the other way. So, any questions on any of that? Okay, shutting that down. So, big picture ideas. Let's do a little bit of review, shall we? What's the big picture here? What don't you do? What's the one way to screw this up? Smush it. How do you smush? When have you smushed? How do you know that you've smushed?
I'm not sure how to explain it better than if you don't have it on both levels, then you kind of assume it would be the same.
If you don't have a time varying predictor slope represented on both levels, then you have smushed. So the exceptions to that is if you have a predictor that is time varying, but it only has time level variance. So when would that happen? It would happen if time is your predictor and everybody was measured on the same occasions, so there's no between person variance. In the example you gave me with vignettes earlier, if everybody sees like 3 control vignettes and 3 treatment vignettes, then treatment is a within level variable, but it doesn't have between person variance. So if it only has within level variance, then it can only have a within level effect. In the same way that a time invariant level 2 person characteristic only has between level variance, it can only have a between level effect. But otherwise, if you're in a situation where you're not sure, how might you test empirically whether you need to worry about this with the time varying predictor? Is there like a model you could run maybe for that? Or like
One of the residuals was there, right?
Do what?
One of the residuals?
One of the residuals.
Yeah, sorry.
Keep talking because I'm not following you yet.
You wrote it.
You wrote it down? Is there a descriptive statistic perhaps that might tell you how much of your predictor is level 2 versus level 1? Yeah! If you're not sure, do that. It's an empirical question. You know, when someone hands me a data set and I don't know what the variables are, I will do that to like, oh, this is a level 2, oh, this is a level 1, oh, this is both, because you can figure that out from an inter-class correlation. What if your level 1 predictor is binary? how would the model have to change? We haven't talked about this. Oh, we talked about it a little bit. Keyword is threshold. All of the models that I've shown you so far are for normally distributed residuals. So if you have a level 1 variable that's binary, then you would need a logistic version of all of this. So you would have to have a link function that constrains the predicted probabilities to stay between 0 and 1, such as a logit or a probit or log-log or one of those thingies. And you would switch out the residual distribution to be Bernoulli instead of normal. Then you can have an intra-class correlation that would be more accurate because it understands that it's a 0-1 variable. And you can replace, if you're in a logit link, the residual variance with 3.29. I'm not making this up. You can. Have you heard that number before? Pi squared over 3? No? That is the variance of the logistic distribution. And so in the model scale, that's what the residual variance is supposed to be. So you can replace the estimated residual variance with that if you are in a logit link. If you're in a probit link, it would be a residual variance of 1 for the model scale instead. So you can do an intra-class correlation on any kind of variable. It gets a little bit trickier if your variable is not plausibly normal. So if your time-varying predictor has variation at both levels, then you need to have an effect at both levels. Alternatively, what if you're like, I don't care about level 2? Didn't someone say that? I only care about the within person? Then how could you solve the problem without having to have a level 2 model? Any ideas? We could get rid of level 2 by doing either person mean centering or latent centering. If you subtract off the person mean, then there is no more level 2 variance and you can just ignore it. Now for me, I'd be like, but you're missing half the story. But that is a common approach in clustered data to de-mean the variables. Basically, they do group mean centering on everything so that they get rid of all the group stuff and they just focus on the within group information. So if you artificially remove the level 2 variance, then you don't have to worry about it. Otherwise, as a general philosophy, you would want to include a version of the predictor at every level at which it has variance. 1, 2, 3, 4, all that kind of stuff. So if we're in a situation up to this point, we've only talked about fluctuation models. What do you think is going to happen if we're in change model land? Does person mean centering work for variables that have individual differences in change? Is the question? It will not. That's the part that we haven't talked about yet. I have 1 or 2 slides on that idea and then a whole bunch of examples of SAM stuff. So in the context of time-varying predictors for models of change, so when your outcome has systematic individual differences in change, you would want to have that in the model. If your predictor also has systematic individual differences in change, then the univariate version where we do person mean centering in boxes is not going to work. Because that version doesn't understand that what we were calling between is at least 2 different things. We would have between person intercept differences, between person differences in change over time, which would be at least 1 variable, possibly more, and each of those things can have a separate relationship with an outcome. Furthermore, if people change differently, then where your intercept is matters. The relationship that it would have with other things would differ if people spread themselves out and the lines cross and things like that. So the model would have to grow to look something like this. This is slide 41. So this is where we were yesterday, the y side, where we were carving up an outcome variable into how much of its variance was due to people start out higher, people change faster, those are both between person variance components, and then why are you off your line today at level 1? Well, if I have a time varying predictor that itself changes, then those 3 things are also potentially relevant for it too. So think about like a hypothetical study where I have some kind of treatment that's designed to improve parenting. And so I'm going to go in and I'm going to make some people better parents and control group, too bad for you. And the parents' skills grow over time, and the idea is that if I become a better parent, my kid gets better at whatever I'm trying to do. Maybe manage disruptive behavior or something like that. So the idea would be that change in parenting skills leads to change in disruptive behavior. So if X is parenting skills and it has change, and Y is disruptive behavior and it has change, then these are all different ways that you can have a relationship between parenting and disruptive behavior. It could be that people who start out lower in parenting skills have children who are worse off, but it could be that people who are able to become more equipped to address their behavior have better outcomes in terms of the behavior. The slope of parenting skill growth could predict the slope of disruptive behavior change. So intercept relationships, slope relationships, and then residual relationships. If I am better than usual in terms of my trajectory, is my outcome different than usual in terms of its trajectory? So I have an example that if we have the strength, I can show you where I deliberately introduced 3 different kinds of relationships between a predictor, and I can show you how they can or can't be recovered with different approaches. Yes?
So can we only include the intercept-intercept relationship? So I was thinking about people who start with high parenting could have a higher slope in what was the other word? So from the intercept to the slope and maybe some other ways around, or is it only intercept-intercept?
You can do anything you want. Yeah, absolutely you can. It would be up to you whether you're thinking of these things as directed relationships, like this sort of causes this other thing, or whether they just are associated. It's all about sort of your theoretical framework and how the variables are represented, but yeah, absolutely. I didn't draw in the cross relationships here because the slide was already packed with stuff, but absolutely you can have those things. So when you get to this level of complexity, you can't do person mean centering on this X because there's no way to get the slope part out of it. All right. Yeah, so the story gets more complex when you have change in a predictor as well as change in an outcome. And there's really no way to do it except for this kind of multivariate, either structural equation model or multivariate multi-level model strategy. There's no way to trick this into a univariate model and have it be correct. That's chapter 9, by the way. So, all right, I think what I want to do here. How are we doing? It's 3 o'clock on the second day. I'm mindful of that. Do you want to see some more of what not to do? Because that's sometimes easier, right? You can rule some things out. So here's some more of what not to do. And I present these because they're still really popular and they're still in the manuals for how to deal with longitudinal data. The problem comes in terms of training, some people are trained in SEM, some people are trained in MLM, and some people get trained in both. And so all of these issues of smushing that I've talked about in multi-level modeling are solved by centering strategies. But the exact same problems are still present in a structural equation model potentially if you're not separating out levels of relationships. It's just that if you're approaching it from that perspective, you may not have heard about centering and think that's only a multi-level thing. I don't have to worry about that in my SEM. but it's not true. So let me show you a couple pictures here. And I have lots of words to go with the pictures as well. So when folks would typically go to an SEM approach is when they're interested in what are known as cross-lagged relationships. The idea that this times X should predict the next times Y, and this times Y should predict the next times X. And typically people want to know, like, which is driving which is the research question that goes with that. So those sorts of relationships are much easier to set up in a single level structural equation model because you've got access to all the observations at the same time, and you don't have to worry about lagging across rows of data, and you can just directly put in whichever arrows going whichever ways that you want to. But the same problems of smushed effects can happen in those sorts of models if you haven't partitioned the variability in a set of repeated measures into what part is between and what part is within. So here are some examples of what not to do. This one. This is called either a cross-lag panel model or an auto-regressive cross-lag model, and it looks something like this. The idea is that we have, say, 4 repeated measures. We have paths from last occasion predicting the next occasion. These are typically constrained to be equal over time. So I do that for Y and I do that for X. I estimate covariances between X and Y at the same time. So this is between their residuals for the outcomes that are being predicted or their original versions for the ones that are not. And then we have these paths right here, which are known as the cross-lag paths. So I'm looking at this picture. Here is a very good paper that describes these problems. It's not the first paper on the topic, but it's probably the most readable, which is why they wrote it, because the other ones are quite difficult to work through. So let me ask you this. This relationship between Y1 and X2, is that within, between, contextual? Smushed, that's what it is. So I don't know if it's because people who are higher on Y are higher on X. I don't know if you're higher than usual, if you're higher than usual the next time. It's all one thing. So the logic is that by including these autoregressive paths, you've somehow controlled for between-person differences. But this type of autoregressive prediction makes a very specific pattern where the relationship decays over time. So if this first path, say, is 0.8, then the implied relationship between Y1 and Y3 is 0.8 times 0.8, which is 0.6. And then if you cube it, I don't know what that is off the top of my head, but it's even smaller. And if you follow this through, the model would eventually predict 0 relationship between one occasion and one that's downstream. But in real data, that rarely holds. There's almost always an intercept component of a constant source of covariance that operates no matter how far apart in time they are. So if between-person differences are not being adequately represented, they're going to confound those cross-lag paths. So they're smush paths rather than within paths, which is what we would want. This one too. This is also a prototypical longitudinal mediation model, where in this case they're thinking that the mediation should take time to occur. And I don't think that's an unreasonable thing to say. So X at the first occasion predicts M at the second occasion, predicts Y at the third occasion. But I ask you the same question. This A path right here and this B path right here, are those within, between, contextual, or smushed? They're smushed, yeah. And the other part of that is that they're missing an opportunity potentially to look at mediation at multiple levels of an analysis simultaneously. You could have mediation among your intercepts, among your slopes, among your residuals, and that latter part can operate at distinct intervals in time at lagged occasions if you wanted to. So it's an incomplete specification. So here's how to fix it. I have a link to the Mplus website where they have a whole page on different articles about this. And the remedy with respect to within-person fluctuation data is to estimate what is known as the random intercept version of the CLPM or the ARCL. It's like letter salad here. And it's exactly what I showed you just a minute ago. You stick a random intercept in here. Typically, they estimate only a covariance between the intercepts because at that point they're just saying between persons we don't know which came first. But critically, this distinguishes the relationship at level 2 from these cross-lag paths now represent the relationship at level 1. So it's unsmushed. What the level 2 relationship is depends on how this is specified. It might be between and it might be contextual. As I said, it depends on the exact version of the syntax. And a lot of people still put in these auto-regressive paths right here, but you may not actually need them. Because part of the reason why X at the first occasion would predict X at the next occasion is up here. The random intercept predicts that kind of constancy over time. So it may be the case that you need these and you may not, but they don't necessarily have to be included if you don't. Here is what that model would look like in, this is Mplus code. This is the code that goes with that previous picture. So I have my intercept for X is a random variable, random intercept latent variable, all one idea, where it's an intercept because all the factor loadings are fixed to 1 for each. There's their fixed effects. These are the random effect variances, covariance. Shut the intercepts off, hold the residual variances constant. Then we can have the first occasion residuals be correlated, the subsequent occasions be correlated. Here's my p-width. So this is x2 with y2, x3 with y3, and so on. And then 2 sets of pawns. So the first one is the autoregressive effects of x and y. So x1 is predicting x2, x2 is predicting x3, same thing with the y's, and then I've labeled these as the cross-lag paths, y1 predicting x2, y2 predicting x3, and then the opposite going this way. So this code, if you had a directed version of intercept x to intercept y, would result in contextual effects because of the way that the residuals are specified, but I can show you a trick to fix it that I didn't come up with, but I know how to do. And here's the Levon code. Does the same thing. I do not know of a pawn equivalent in Levon. Does anybody know of that one? Do they have one? No, so I had to do more typing, basically, is what it amounts to. So I wrote out all of the individual autoregressive paths and all of the individual cross-leg paths, and they're held as constraints via these labels. Same thing with the residual covariances. Okay. Yes?
I don't get why it is okay in the random intercept process panel model to set the autocorrelated path to be equal, but not in the normal project panel model. This assumption, or maybe I misunderstood you, because you said in the beginning that this assumption to set them equal isn't appropriate in the normal project panel model.
Typically people will start out with that constraint where they're all the same, but potentially release some of them if it looks like it's causing a problem for model fit. My point was that these autoregressive paths you may not even need anymore after the random intercept is there. And I think it's an empirical question whether they can be constrained to be the same or whether they need to be different. But this idea would just be that residuals that are closer together in time are more related, and residuals that are further apart in time are less related. But the related is a very particular pattern when these are all forced to be the same, where there's a decay, because it's R for, it's an estimated correlation at lag 1, it's R squared at lag 2, R to the third power at lag 3, and so forth. But part of the reason that they would have been related is now up here. So this relationship will be a lot weaker than it would have been before. From a theoretical basis, these autoregressive paths have always been really dissatisfying to me, because it's like, what predicted it at time 4? Well, time 3 did. What predicted it at time 3? Time 2. What predicted it at time 1? The first occasion. What predicted it here? Like, I don't feel like these are useful in terms of an explanatory perspective. But it's very like hard baked into when these models are estimated, people just start with this because so much of the time that's how they've looked. But the random intercept frees you from the constraint to necessarily have to have this part. Does that answer your question?
Yeah.
Maybe?
Yeah, maybe.
Maybe.
Yeah, maybe I don't understand the interpretation of this auto-regressive.
You and me both. You and me both. See, I'm bothered by the fact that the simultaneous relationships are covariances and not directed arrows, because you're predicting how last time predicts next time without controlling for this times. And so it's incomplete from my perspective, but this is almost always what it looks like. So what if either of these variables changed systematically over time? Could that happen? Like parenting skills could improve and disruptive behavior could improve? What do I have to do to this if that's the case? What should I add? That's one idea. I could turn this into more of like a measurement model latent variable where I would estimate some of the loadings. If I wanted to specify a change with a particular functional form, as an alternative, I could add a latent variable. So I don't have any slopes here, random slopes for change over time, but I could stick them in here, couldn't I? Absolutely, I could. So in transitioning to contexts in which there are individual differences in change over time. If it's just a fixed slope, you can put time in as a predictor and call it good. But if there's a random slope that varies across people, then that has to be a separate variance component in some capacity beyond the intercept. So in those sorts of models, you will still see a couple of variants of time-varying predictors that are incorrect. I have an example that is sort of a shortened version. I have a longer version in a previous class that I taught at the University of Kansas, which is coming back to Iowa in the spring. But here is an example taken directly out of the Mplus user's guide, and I just checked 2 weeks ago and it's still there. This is an example involving a time-varying predictor. So in this story, Y is an outcome that has individual differences in an intercept and individual differences in a slope for change over time. I've got two time-invariant predictors labeled as x1 and x2. So part of the reason why people start out differently and change differently is because of x1 and x2. And then I got this variable a here. Nope, come back. A, at one occasion, predicts the corresponding outcome at the same occasion. So any guesses as to why I'm saying don't do this? Is this path the between effective A, the within effective A, or the smushed effect? It's smushed. And I'm not just going to pick on Mplus. Here's the same picture in Levon. Stole this from their website. It's labeled differently, but it's pretty much the same picture. And here's the Levon code that go with it. These paths are smushed. So how might one fix it? Well, here is one example of something interesting that happens. If you allow the time-varying predictors to covary with the intercept and slope for the outcome, it turns out that that unsmushes the paths. So Patrick Curran and his colleagues figured this out about 10 years ago. I had not seen that happen. They gave some algebra as to why it is, and I don't do algebra. I just say, okay, I believe you. But if you include these covariances, then these paths are unsmushed. However, what's missing in the model is the between effect. We don't have a way to get the between effect of how z relates to y because that's not being represented as its own variable. And you can't throw the person mean in here as a separate box because it's redundant with each of these individual boxes. There's no new information there. So he's like, well, I'll just put an intercept in. No biggie. So this model is sort of a compromise between the models we've looked at where y is allowed to have individual differences and change via this random slope factor right here, but z is not. So this would be a situation in which the time-varying predictor fluctuates over time, whereas the time-varying outcome has individual differences and change. But now we can have the z-intercept factor predict the y-intercept factor and the y-slope factor, and we'll get level 2 relationships here. And we can have the individual time-varying measures of z predict this corresponding individual time-varying measures of y, and I'll get a level 1 relationship. However, if we just have z directly predict y, then these effects over here are contextual. That's what we saw earlier today. If I just have the observed variables predict each other, then what happens at level 2 is contextual. So he figured out a workaround, which is represented by these little circles right here. It's the same workaround that I had to do to demonstrate the latent variable interaction. It's what he calls the term structured residuals. The idea is that I'm going to take the variability that is residual in each of these time-varying predictors, so it's left over after the intercept, and I'm going to move it to a new latent variable. It is literally just a relabeling. So in terms of the code, what you would tell it is, okay, shut off this residual variance and put it over here. So you're defining a new latent variable that would be perfectly measured by these and pushing its variance over to it. And then Mplus is like, oh, well, that's not part of this thing. That's its own separate variable that only has within information. So if the new variable only has within information, then that changes this part of the model into a between effect instead. So this additional layer of renamed variables, essentially structured residuals, then allows us to have the between level interpretation that we would want up here. And then here is the symmetric version of this model he published subsequently, where we have slopes and intercepts for y, slopes and intercepts for z, and then we have the relationships for the cross-leg part here through the structured residuals in the middle. So then this is a better version of the picture where you asked if I could have the intercept predict the slope and the slope predict the intercept. This part right here you can do whatever you want with. You can have them covary, you can have them be directed. They will be between level relationships if you move the residual variances to these new layer of latent variables in the middle here. And this is also something that I discussed in the 2019 paper. This is one of the options that is described in there. So this is how we would do time-varying predictors in a structural equation model. We unsmush their effects by directly representing via separate latent variables between person sources of variation in intercept and in whatever change over time that we have. Question?
Yeah, but when I have latent variables instead of that, for example, then the epsilon part is like the residual variance of the latent variable in this case. So I cannot apply this logic to a model with latent variables and like items at each time point.
So are you asking if these were circles instead of boxes?
Yeah.
Okay, so then it would be like what they would call a second order latent growth curve, where the factors would be growing over time.
Mm-hmm.
And so then your question is what again?
What is epsilon in this case, or where, from which variable? From the latent one, from the circle.
So what happens is we would say that your factor
Mm-hmm.
is being predicted by the intercept and slope.
Mm-hmm.
Okay? So that means that what it has left as its variance is only within person variance.
Okay.
We then define another latent factor and transfer that within person variance to the new latent factor.
Okay.
And because it's viewed as separate, that means that it's only level 1 variation that's predicting the other thing. The level 2 model switches to between, the same as it does with person mean centering.
Okay. But in this case, do we also have like item-specific residual variances in the model?
You would,
Yeah.
as long as the items are treated as normal and not, an IRT model or something.
No. Okay.
Mm-hmm. Yep. Yeah, at that point, I think you would need a lot of data to pull something like that off with all the layers of latent things. But because this isn't really a latent variable, it's just a renaming.
Yeah.
There's no extra parameters being estimated. It's just a trick, honestly. It's like tricking Mplus into behaving itself and getting what we want out of it. It's not a true latent variable in the sense of representing the commonality, because it's indicated, each of these is indicated by one thing. Sure, but doing this sort of trickery then limits the other stuff that you can do. And so that's why what I showed you was the idea of just asking for what the between effect would be using model constraint. So all of this middle ground here, trickery, is just to get these to switch from contextual to between. You can just ask them, just ask for what the between is, add it together. And it's less painful to set up the code. But I've got an example of how one would go about doing this. All right. I have another paper that I stole this picture from just to highlight the idea of what longitudinal mediation could be. And this is real data. I was like 4th or 5th author or something, but I did all the figures for it and helped with the analyses. So this is more of a conceptual diagram than a mathematical one. This is sort of designed to illustrate the ideas. So this was a study of children where they had time invariant predictors of their anger and their effortful control at 54 months, which is roughly age 4.5, so before the kids would have started school. Kindergarten starts at 5, I think, in most cases, and you turn 6 during kindergarten. And they wanted to examine the extent to which the effect of these variables on subsequent externalizing behavior was mediated through teacher-child conflict. So in this situation, I've got teacher-child conflict as something that changes over time. So some children have more conflict as time goes on and some have less. So I've got an intercept for where they would be at time 0, as well as a slope factor. And these were estimated as a latent basis model, so that the factor loadings were estimated to get a nonlinear change. Then I've got 2 different sets of outcomes. I have externalizing behavior as reported by the child's teachers and externalizing behavior as reported by their parents. And both of these show change over time as well. Some kids increase in externalizing problems and some kids don't. Some kids may go down even. So I have M's that are longitudinal, Y's that are longitudinal, but X's that are only level 2. That means that at this between person model up here, there are many different ways that these things can predict each other. The ones that are in bold are the ones that were significant. So there was significant mediation of the relationship between younger effortful control and subsequent externalizing problems going through the teacher-child conflict intercept. So there were 4 different paths then that were of interest in this, as well as a number of other significant direct paths. And I'm not a developmental psychologist, so I can't tell you why this is important or noteworthy. I can just tell you this is what we did. So this is what I would call longitudinal mediation. We're talking about how initial status or ending status, you can define your intercept however you want, relates to subsequent change and how that relates to your behavior earlier on. Then the within part of the model is in this little box down here. Because X was not measured repeatedly, there is no way to show within-person mediation. All I have are directed relationships between the mediators and the outcomes. So it's subsequent information. We're looking at the association of the residuals at the same grade and the prior grade. So if you have greater conflict at one grade, does that sort of follow you to the next one? Is kind of the question. And it looks like in some cases they did. So that was the within-person part of the story. The between-person part of the story was the primary emphasis. And I've got a link to where the paper is if you're interested in looking at that. So this is how I would do longitudinal mediation if both M and Y had individual differences in change. What else do I got in here? Words. I got a lot of words. So yeah, because I knew that we'd be like, have lost our wills to live by this point. So I've got lots of words for all the things. So this is sort of a pros versus cons on how to set up the Bing models. But the big picture is that any variable measured longitudinally has both between-person differences and within-person differences, and they gotta both be in there. And if the variable shows change over time, then we've got to have random slopes for that as well. That's the big picture. Do we need another break? Maybe? Yeah, small break? Okay, let's take another small break, and then we'll see what's left. How's that?